So in the last class, I told you that I would be discussing transfer function in this class, but I think I need to clarify that wherever I wrote y0, I meant initial condition, right? So I think I should have written f0 because f was the function. So y0 actually means f0 there. So please correct yourself in your notes if you are making any, or you will just consider it to be f0, right? So today I will be starting with transfer functions. So I will be introducing the concept of transfer function using the same our favorite example of a single degree of freedom system. So we know that single degree of freedom system equation of motion is given as mx double dot plus cx dot plus ax is equal to the force acting on the system. There is some force acting on the system, isn't it? So what I will do is I will take Laplace transform on both the sides. So taking Laplace transform on both sides. I'm taking Laplace transform on both. So what I'll get is, so m is a constant, so m constant will remain a constant. Anything multiplied by the function remains same in the Laplace transform. Right? Times x double dot. So let me assume here that Laplace transform of xt is equal to xs, capital Xs. So what will I get here? M times, this is double derivative of x function, xt function. So I get m s square times xs, isn't it? The property that we introduced in the last class, m s square times xs minus s times x naught minus x dot initial velocity, right? This is the Laplace transform of this term, right? Isn't it? Plus Laplace transform of this term. So this will be c. This is a single derivative of x, so there will be only one s times xs minus s times x. This is the Laplace transform of this term plus Laplace transform of this term will simply be k times capital Xs is equal to Laplace transform of ft, the forcing function. Let us assume that that is right. Now I will assume that the initial conditions are 0. I assume that initial displacement and initial velocity is equal to 0. So what will I get? This will disappear, and this will disappear. So what I will be left with is this, right? So this I can write down as, I can take capital X as common. Inside I will get m s square plus cs plus k. This is equal to what? Fs. And doing more mathematical massaging of this, what will I get? That xs upon fs is equal to 1 upon ms square plus cs. This is what I will get. So what is this? This is nothing but, let's say, the displacement of the system, displacement of the single degree of freedom system is the output of my system. Let's say this is the output. And this forcing function is the input to the system. We are defining it as an input to the system. So this Fs is the, let's say, is the input to the system, and this Xs is the output of the system. Output, by output I also mean the control variable. So a ratio of Laplace transform of output of the system divided by the Laplace transform of input to the system, the ratio of Laplace transform of output from the system and input to the system is actually called as the transfer function of the system. Is actually called as the transfer function. And in block diagrams where we showed the that this is the system, block, I said this is the system block, or you can call that this is the plant block, or you can call that this is the process block. We can now actually replace this by writing this. And input to this is Fs, and output to this is, right? So this is where the Laplace transform plays an important role. Because we want to go to this type of notation in control engineering, that is where Laplace transform comes in. It gives us a very convenient form of putting things in the block diagram. Right? And this is only possible because of the Laplace transform. Right? So now from now on we'll try to find the transfer functions for different processes which we generally encounter. Right? Thank you.